Alright, in this video, we're going to estimate the value of pi. We're going to do so using a Riemann sum and the equation for a unit circle. Now, the first function to find here is called height. And it's called that because it finds the height of the unit circle at the given x point, which is going to be a point between 0 and 1. That can be used to find the area of a bar in a Riemann sum. Bars are what I like to call subdivisions. And bar x in that one, bar x is the midpoint of the subdivision, and n is the number of subdivision in the Riemann sum. So basically multiply height x times the 1 over n, which is the width of any bar, n being the number of subdivisions. Anyway, now we've got this function STN. ST is short for estimate, and this one has a for loop and a sum accumulator in it. So we set the sum accumulator to 0. I'm going line by line, and then for I in range n, we find the x value of the midpoint of each bar, and then we find the area of the bar, and then we add to the sum accumulator for every bar in the Riemann sum, every subdivision. And now we've got error function. Error is short for error. I've got the approximation of pi that you see there is from a math module. I just printed it out to simplify things, but it's the same estimate that math module uses. I checked, and the approximation. Remember, we only approximated a quarter of a circle, the area of a quarter of a unit circle. So we've only approximated a quarter of the area of pi. So we have to multiply it by 4 to get the area of pi, which it does that. And this function, I wrote so that it returns percent error as just a fraction, just a decimal. Like for 1%, it would be 0.01. And I wrote that way because I like it that way. I like to do math that way. And so now we've got this function pretty. Now pretty is called that because it makes the output pretty. And I'll explain what each line does. This one, just STN, the area according to the Riemann sum of a quarter circle, and then multiply it by 4, and then round it to 5 decimal points because that's how you want it. You want it round to 5 decimal points. And it just says this program estimates the pi at area being the area of pi, 4 times STN. And then you can pretty much see what it does based on the green code, the text. And then it calculates the percent error and then rounds it to 5 decimal places and prints it out. Now, last but not least, we've got error bound. Error bound is short for error bounds because, well, it calculates the error bounds, and it calculates how small a number of bars can we have in our Riemann sum for the function SDN, and it'll be within 0.001, that's 1/1000th of a percent accuracy. But since I wrote error function the way I did, I've got represented as 0.0001, 5 decimal points instead of 3. And it finds the least amount of bars that is accurate within 0.001%, and says winner. So yeah, that's what that function does. Okay, now that I've explained all the helper functions, I'm now going to run them. So you want me to do it with 2 bars, 20 bars, 200 bars, and 2 million bars, right? So I'm going to do that right now. Okay, estimates pi around 3.25937. The percent error is around 3.7%. Okay, let's try it with 20 bars. Okay, it's looking better. 3.14543 and a error of 0.11221, so about 1 part in 1,000 is there. Okay, that's pretty good. Now, pretty 2000. This one has a very low error, very accurate assessment. Now, let's try 2 million. This one's going to be really, really accurate. Accurate enough to actually use. Yeah, it takes an extra second because it's calculating so many bars. But only 1 extra second, not 2 extra seconds. Computers are cool. Anyway, so we've done that. Now, let's answer the last part of the question. What's the minimum number of subdivisions that will be accurate within 1/1000%? And the cool thing about Airbound N that I forgot to mention, it's any arbitrary large number, because the for loop has to execute a bunch of times, and it just has to have a stopping place because it's not the Big Bang. It can't just go on forever. It has to stop somewhere. So just give a place to stop. Let's say 1,000. Maybe we'll get lucky. Winner 494. So if you want this accurate within 0.001%, use about 500 bars. So that concludes our video. Thank you. And it's been fun making this.